So this page is the key result for our discussion of adding a angular momentum characterized by a quantum number L to a spin half situation where S is always half. The allowed values of J is L plus half and L minus half if they are positive. There's a case where we have to foul out a negative possibility, which is the S state. If L is 0, then J is half only. So this box summarizes everything. So last time we illustrate this rule by considering a P state, L equals 1, and doing some accounting. We found that no more, no less. In either way, we have labeled it 6 states. It is just a different ways to label the 6 P states. And then mathematically, for those students who think about physics rather theoretically and mathematically, it is just 2 ways of labeling the 6 states. Thereby, one way can be found as a linear combination of the other 6 bases. So here, equation 23 illustrate from the labeling of the Z component of L and S, so ML, MS, we can move to a new total angular momentum description on the left-hand side, J, MJ. They are just linear combination. Thereby, there are coefficients we found. In our course, we will not go into the details of how to find the coefficients. They fall into a topic of addition of angular momentum in quantum mechanics. This particular set of coefficients are called Kapsch-Gordon coefficients. They will be discussed in more advanced quantum mechanics course that has to do with technical detail. Here, we want to apply quantum mechanics to understand phenomena. In particular, we have some discrepancy in the spectroscopic data in hydrogen and other atoms we want to understand. So we also emphasize that we have 2 ways of describing these 2 sets of 6 P states. Which one is better? The proper answer, the logical answer is it depends on the situation. Next section, we will discuss something called the spin-orbit interaction. When this term is here as a perturbation, it takes on the form S dot L. Immediately you see, if we state on the description using the Z component of S and L, that will be problematic, right? Because S dot L means there are SXLX term in this combination, SYLY term in this combination. Immediately you see that, for example, LZ is not commuting with LXLY. So that description will be very difficult to handle this dot product. It will not be convenient, okay? So the set of using total angular momentum J, MJ, will be much more convenient when we have this term in hand. We will see it in the next section. So here, I want to make things just being plausible. So we can think about why this rule is there. Okay, so we have a S state, the longest angular momentum projection on Z is 1 h bar. We have a spin half, so the longest in the positive Z component is h bar over 2. So for these 2 Z component, if we add them up, the longest total angular momentum Z component will be 1.5 h bar. So it is 3 over 2. Once we have this MJ, because angular momentum Z component runs from plus 3 over 2 instead of 1 to minus 3 over 2, there must be a J value corresponding to 3/2. You cannot escape that, okay? And then we know there are 6 states. So this accounts for 4. There are only 2 states left. Within this description, the other j can only be half because mj can only take on 2 more values. Thereby, our rule makes sense. In a pictorial way, what we just said is the following. In this case, we have a Z of L that is the longest. The Z of S, again, is the longest here, half, okay, half H bar. Then we add them up, thereby J is very long, and that is the 3/2 case. The spin could point in the other way. Remember, spin half means a cone up there, that is this direction up there. You take any one, it will be tend to point up. There's another cone go down, okay? So it is this case, and that will give us the shorter J situation. Again, this is just a model. Don't take it too seriously, but it is an artist's way or artist's impression of quantum mechanical result. Although it is just a model, I have seen generations of experimental physicists make use of this model very cleverly and invent very nice things and very nice work from this picture so that they could go into rather deep spin physics. In particular, I'm saying using it for memories, things like that. So we ended there. So today's plan is as follows. We will first clean up this part on addition of angular momenta, and then in particular at the end of this part, we have a few pages on adding 2 spin half entities. That turns out to be important nowadays because you have a lot of things to play with spin half situations in the so-called second quantum revolution. Then we will move on to the physics of spin-orbit interaction. It's a very interesting piece of physics and turns out to be increasingly important in recent years. And then after that, we will discuss the consequence of having spin-orbit interaction. Okay, so I type up the plan for today. So the first thing to note is the following. We have defined J, total angular momentum is L plus S. We also discussed for L, there is a magnetic dipole moment going with it. They anti-aligned because of electron has a minus E charge by convention. Nonetheless, this is anti-parallel to L. Similarly, there's a spin magnetic dipole moment that is anti-parallel to the spin angular momentum. Now, we have defined the J to be L plus S. It is interesting to look at the total magnetic dipole moment. Naturally, it is defined as the sum of the 2 magnetic dipole moments. Each one can be written down. Okay, now remember, there's a difference in the G factor. The G factor for orbital angular momentum here is an invisible 1. So this G factor is 1. But here there's a G factor that is a 2, canceling a definition of 2 here. That's why you have a different prefactor. Because of this difference, you factorize out a common factor, you actually get L plus 2S. Okay, so this equation is formal. Total magnetic dipole moment associated with orbital and spin angular momenta is equation 24. Important observation. Formally, this is not antiparallel to J because L plus S is J. L plus 2S is not J. It is J plus S. There is something a little bit more. All right. Now, that is some problem to handle in the future. It would be nice if the total magnetic dipole moment is really antiparallel to J. Okay, but the hard fact is that formally it's not. Nonetheless, later on, we will try to make an approximation. Our course is about making a lot of approximations. So we want this to be the case. The question is how, right? So we will discuss it later. Let's say if we can argue that this is a good approximation, then some nice thing will happen. For example, we have seen this J has a quantum number that could be 3/2, right? 1.5. Then if we apply an external magnetic field, we know that that will split the MJ degeneracy. We discussed such a physics in Zeeman effect. If this is the case, then we can get even number of splitting in a spectral line. Something that we mentioned previously, that the normal Zeeman effect, 1 line into 3 line, is abnormal, is not usually or normally observed. Instead, more often than not, one spectral line split into 4, even 2, 4, even 6, even 10. Now we have a way to get at that, provided that we could make some approximation here that the total magnetic dipole moment is antiparallel to J, although formally it is not. All right, so take this now. First of all, fact, it is not. Second, later on, we try to make it that way, make an approximation, then we can get at some comparison with real phenomena. So here, just summarize what I just said in a clean page, take home message. Here is an important extension. I include here for the reason that nowadays it is quite a hot topic, adding 2 spin half angular momentum. So we are generalizing things. We have L orbital add into a spin, but nonetheless, our emphasis has been that angular momentum obey the commutation relations. It doesn't matter whether one must be an orbital angular momentum or not. Thereby, we would like to discuss, how about that? We have 2 spin half thing. I want to add them up. What happened? Okay, so let me define the situation. I have something called a spin number 1. Okay, AM is angular momentum. So spin angular momentum number 1, and this 1 is meant to label number 1. All right, it's not a X, Y, Z component. It is number 1. Spin half means the quantum number S1 is always the boring half, and then the Z component has 2 possibilities. Similarly, I have a spin angular momentum number 2. The Z component can be up and down, plus minus half. Then I want to add them up, define a total spin angular momentum. You may wonder, in what situations this will be applicable? Think about helium atom. You have 2 electrons. Each electron has spin half. So you have a situation where you have two spin half electrons. We want to define the total spin angular momentum of this two electron system. All right. In this situation, we need to know how to add two spin half electrons. Okay. Although the applications nowadays is much wider. For example, you have two photons. You can add them up. Okay. So two photons, they are stuck together when they are born, and then they fly apart, things like that. You need to know something about adding two spin together. Photons is spin one, right? So let's say we define this total spin. Well, this is angular momentum, this is angular momentum, no doubt this is angular momentum, all right? Any operator of 1 has nothing to do with any operator with 2. They operate on different things. So when this satisfies the commutation relation and this satisfies the commutation relation, this must satisfy the commutation relations. Thereby, this is also an angular momentum. Needless to say, S squared must be of this form, and given as Z component can take on S to minus S instead of 1, things like that. Okay, now easy. We copy result. All right. The question is, what are the values of S given S1 is half, S2 is half? Okay. So we copy result. We pretend this S is just an L, so we have a L plus half, L minus half. So we have half plus half, half minus half. So the total angular momentum quantum number, this S is this S here, all right, can take on 1 and 0. Behind 0, there's a MS, JMJ, that is the MJ, okay? That is 0, so it's only one state here. However, here, the MJ will be 1, 0, minus 1. There are 3 states here. Altogether, there are 4 spin states for 2 spin half things. Makes sense. Separately, in the 1 and 2, not adding them together description, you will have plus half for up, 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 down, down, up, and down, down. You have 4 states. That is one accounting scheme. You add them up, you have the total spin being 1. Behind it there are 3 states. The Z component is 1, 0, minus 1. Here you have 1 state, altogether 4 states. No more, no less, as we discussed. Obviously, the 2 accounting scheme, one must be a linear combination of the other, and vice versa. This must be a linear combination of the other. You see, no new physics if you understand the physics. So here is just what I said. Let me introduce 2 names that are important in the context of molecular physics and also nowadays in quantum sensing. I don't know whether some of you are working on nano diamond nitrogen vacancy center in nano diamonds. There are 2 groups in the department working on that. Okay, and you will need this triplet state, these names to go forward. They are just names. The meaning is that S equals 1. There are 3 possible Z components. 3 means trip, right? Triangle, triple, okay? So this is the triplet states. There is a S equals 0, only 1 possible Z component. That means there's nothing there. The sum is 0. There's no vector of the total spin. It disappeared. And then there's only 1 state. singlet state. Altogether 4 states, okay? As I said, no more, no less. If you don't add them up, you will have 4 combinations anyway, right? Therefore, you linear combine this 4, you will get this 4, all right? Now, there are some very straightforward way of thinking about it. This is half, half, up, up. So for the 2 spin, the spin live in the upper cone. So the Z component, if they're added up, that must belong to this one. That's the only possibility, right? Similarly, down, down, it must be this possibility. So thereby, the only thing left is what happened to these 2 states. We now know these 2 states must correspond in some way to this state, s equals 1, and this state, s equals 0. Okay, so this is what I just said. So it happens that we can do a linear combination of up, down, down, up. This particular plus combination will give us the triplet state with Z component being 0. The minus combination gives us this singlet state. Here you see there are coefficients. It is a 1 here, 1 over square root 2 here and there, and there's a minus 1 over square root 2. So these are what I just called the Kapsch-Gordon coefficients involved. Here is an artist's impression of what we just discussed. It is a picture. Don't take it too seriously, but many physicists take it slightly more seriously and then can think out a lot of interesting physics to do. So here is just the picture about how we have this triplet and a singlet state. I think it is easy to visualize the s equals 1, the longest Z component state. Both spin live on the upper cone, and their Z component are both aligned upward. You add them up, it is a longer Z component, all right? And then the total spin must be longer, living in a longer upper cone. That's easy to visualize. Similarly, the triplet state has the longest minus Z component, ms equal minus 1. It's just, you flip the whole thing down, it's the same thing. Now, more interestingly, is how the artist's impression to draw the 2 ms equals 0 state. However, they are different. One has a long total spin angular momentum. The magnitude square here, okay, is square root 2 h bar. It's not 0. How to make a picture of it? I would like you to focus on how these 2 things cooperate. Okay, let me show you. In this particular state, the vector model picture, the 2 spin half live on this cone in a rather coherent way. So every moment they are like this. Okay, now in this way, the Z component cancels. That gives us the ms equals 0. However, along x, okay, or y if you like, actually there is a non-zero thing. All right, but we don't know where it is. Well, you have done all this calculation in spin, right? The expectation value is 0. All right, so because on the cone we don't know where it is, on this cone we don't know where it is. All right, it's like this. It is doing some precession. So the point is that in this case, the two spin half, they cooperate in how they point, so that there is a magnitude surviving on the x direction. Quite long. That's why it is a s equals 1 situation. Let's look at the singlet situation. Okay, in the singlet situation, they also cooperate, but they cooperate in a way that they always cancel each other so that there's nothing left. You see, the upper one spin point this way, the other one point exactly in the opposite direction. So they cancel each other, one add to the other one becomes 0. And that is how the artistic thing to depict what happened in the singlet state. Again, it is just a picture to represent the quantum mechanical results. Now, it is some interlude to later applications. So one application is in helium atom. Although we haven't discussed how we can do quantum mechanics on 2 electron atoms, helium, I think many of you had chemistry in high school or in your year 1 chemistry 1070. Okay, and in that situation, you know that the ground state of helium is that 2 electrons, they both are in the 1s state. And then Pauli said they should have different quantum numbers. Therefore, you usually write 1s, 1 up, 1 down. Okay, now by that you also mean if this is the 1s state of the helium atom, you want to put the 2 electrons up, that is spanned. And it is spanned by Pauli exclusion principle. Therefore, following our discussion, the ground state is not a spin triplet state because this one must be corresponding to s equals 1. Therefore, the ground state must be a singlet spin state. And therefore, you usually see this picture. But this picture is problematic by itself. You could ask, you have 2 electrons. Is electron number 1 spin being up or electrons number 2 spins being up? Which one is up, which one is down? The logical answer is that the 2 electrons living in such an atom, they are identical. How can we label them? They are not red electron, green electron for us to label. They are indistinguishable. In Chinese, 不可分辨的，不可分辨的. This indistinguishability of electrons turns out to be a very important point in quantum mechanics. We will have more to say about that later, but here we already know the proper answer. If we want to write down the wave function, including the spin wave function out, it should be a linear combination of 2 possibilities. Electron number 1 up, electron number 2 down, minus electron number 1 down, electron number 2 spin up. That is the proper description of the spin of the 2 electrons in the ground state of a helium atom. Now, that is something new knowledge that we point out today, only after you know how to add 2 angular momentum. Extending it a little bit more, how about helium excited state? Well, we use the picture of hydrogen atom pretending it is applicable to helium. So we have 1s, then 2s, and 2p, 3s, and so on. Excited state means high energy. So how about this? 1 electron in 1s, another electron in 2s. Makes sense That is an excited state description. And then we want to include the spin description. Thereby, there can be 4 possibilities, right? So you have spin, up, down, up, down. Now, first of all, Pauli allows all this possibility because the 2 electrons are now in different atomic states. The quantum numbers are already different. So the spin can be anything. All right. So obviously, you know that this is a spin triplet. This is a spin triplet. And this too should be more careful. Again, we cannot distinguish which electron is which. Thereby, we need to do 2 linear combinations. One is a triplet state, another is a singlet state. Therefore, we found that helium excited state, there are 2 possibilities. There's a spin triplet, there is a spin singlet. The question is, which one is the actual lowest excited state, the first excited state? Then we need some experiments. Spectroscopy comes in to help. And in answering that particular question, turns out open up a big industry. Only when we understand that question, the answer to that question, we understand the origin of magnetism. Why we have magnetic materials in the world. And you know, magnetic materials, I think, is the most money-making materials next to silicon. Okay, you use a lot of magnetic materials every day in your hard drive, in your memories, memory sticks, things like that. Okay, but the origin of the understanding of that thing has to do with the understanding of the helium excited state. We will have more to say when we go to many electron atoms later. Okay, so here is just giving you a roadmap for some student who want to learn more, go further than the scope. There are higher level topics to do. I already mentioned how to find out all these linear combination coefficients. And then what I just told you about the origin of magnetic materials is under the name of the Heisenberg exchange mechanism. We will see, is the triplet state preferred to be lowered or the singlet state? If the triplet state is preferred, it means the 2 spin tend to align, tend to cooperate in an aligned way. And that is the origin of magnetism. You see Heisenberg is there, okay? So here I already mentioned it, but one more point I want to make before we go back to spin-orbit interaction physics. It is just a very brief description, because it is the first time here you see something called entanglement. So these 2 states are actually entangled states. What do I mean by that? Now, if you have 2 spins, somehow if they bond in this form, you look at spin number 1. There's a question posted. I will do that a little bit later, all right? Now, let's focus on the first entry. That has to do with the spin number 1. If you have a state, there's the 2 spin bond in this form, okay? Then spin number 1 can be up and can be down. That means it doesn't have a reality, meaning it doesn't process a property of the spin. projection in the Z component, okay? And then what happened depends on some measurement on the other spin. Now, if you make a measurement on the second one, if it turns out to be down, immediately the first one is up. If it turns out to be up, immediately the other one must be down. You know, you have a linear combination of things. You realize this, okay? The wave function collapsed to this term, right? So you measure this and then this is realized, okay? Now that is what we call entangled state. You see, in this particular triplet state, this one, the two spins are entangled. Similarly, for this singlet state, the two spins are also entangled. Now, here, we don't need this thing to understand helium. We don't need that, okay? Well, but I just want to say, this thing is around since 1930. Only after 90 years, 80 years or so, we have a lot of new experiments playing with this. There are situations where you have a source here, two photons, there are two photon process coming out due to conservation of linear momentum. They must fly apart, okay? But they are born in a way that their angular momentum must be either this or that, okay? Then each one of it fly apart. So very far away, you measure this, immediately the other one knows its fate. What properties should it take, okay? And this kind of experiments have been done over the past 30 years or so, clean up a long time question in fundamental quantum mechanics, whether quantum mechanics is local or non-local, okay? Things like that. Well, go into philosophical questions, but it is at the heart of something called the second quantum revolution that's happening now. The first quantum revolution has to do with the Schrödinger equation and its consequences. So we have quantized the states, we understand magnetism, we understand semiconductor physics, then you have a lot of nice things now. But there are things in quantum mechanics that we haven't made use of up to now. Superposition is one thing. Here you see that. Entanglement is another thing. So-called second quantum revolution nowadays have to do with making good use or making money out of these two properties that have not been explored or exploited yet. Okay, many countries in the world, the US, the UK, China, Europe together, they are investing a huge amount of money into what we call the second quantum revolution industry or business. You should take note of it because this is your generation's opportunity, especially as physics students. You know much more quantum mechanics than the engineers. The engineers now, they are trying to learn quantum mechanics, but they, you know, traditionally they don't have that background, okay? They want to catch up, but you have this background, but you also need to realize the opportunities out there for your generation. But I will stop here, okay? I'm not doing quantum optics, quantum sensing, quantum whatever here. I end this with further extension, okay? So what if I'm not adding spin half? So that could be L add to a spin one thing, how to add. So I give you the rule. It is the rule to do it. Again, total angular momentum is the angular momentum. You have all this rule. The whole thing is to determine what is J. And this is the rule to decide what is J. It is easy to count, at least, to make sure that the two descriptions are accounting for the same number of states. You will have some problems to count to make sure that no more, no less states are included. Okay, so what's next? We will start our discussion on spin-orbit interaction. In this case, you will see the total angular momentum accounting system works much better than the individual L orbital and the spin description. Therefore, we need the knowledge about total angular momentum in order to handle spin-orbit interaction. Okay, so this ends this part. Let me start a few pages on the next part before we take a break. I want to lay out the big picture first. So this is a very big business nowadays. It's just so happened in condensed matter physics. Originally, it was about atomic physics, the fine structure in atom. Then it get into semiconductor physics in the 1950s, 1960s. Then it became quiet. In the past 15 years or so, the condensed matter physicists suddenly found that spin-orbit interaction become, again, very important in the lower dimension materials. Nowadays, there's a lot of things called topological insulator, very fancy thing. And suddenly, everybody goes back to learn spin-orbit interaction. So given this atmosphere, I rewrote part of these things, and then this discussion is more complete than what is only needed for atomic physics. Because some of you may be going into some fancy things, quantum spin liquid, a lot of fancy things, but this is the basic background. So what is spin-orbit interaction? The whole picture, very simple, is here, okay? Be very sure. It is about the electron's motion generating a magnetic field acting on the same electron's spin, okay? Let me repeat. It is an electron's motion generating a magnetic field acting on its own spin. So it is its own orbital motion interacting with its own spin angular momentum or spin magnetic dipole moment. Then you may think, what is the role of the nucleus, right? The nucleus is responsible for providing a potential energy term. You know, the Coulomb potential energy term, okay? So the complete story is as follows. An electron moving in a potential energy landscape provided by the nucleus will generate a B field, a magnetic field interacting on its own spin magnetic dipole moment, okay? Now it's easy to think that at the end, it must be like this, right? The orbital motion generates something like a magnetic field that got into its own spin. Okay, so you will have a term like this. This is called spin-orbit interaction term. The end result is that after we understand the origin of this, after we do perturbation theory with the total angular momentum new basis, the new accounting scheme, we can understand why in the real data, the two p states are not all the same energy, but split into something like this, tiny splitting. that is called the fine structure. All right, so that is the big picture. Okay, so here is the same thing. Electron moving, you sit at the electron, it's like the nucleus moving. The nucleus moving is a positive charge moving, it's like a current loop giving rise to a magnetic field at the place of the electron. The electron has spin, magnetic dipole moment with an internal field. Dot product is an energy term, thereby you have S dot L. So that is the physical picture, all right? So the key points up to here before I stop for a break is the following. First thing, we are not talking about an external applied field. We don't need a magnet. There is an internal magnetic field, okay, generated by the motion of the electron. It's free of charge. Even if you don't like it, it is there. That's the problem. We need to learn a lot of things in order to understand that, okay? And then its motion gives rise to an internal field that interact with this electron's spin magnetic dipole moment, giving rise to a term like this. Then we learned in the previous module, when we have an additional term called spin-orbit interaction term, the total Hamiltonian is now modified. So we have a classic situation. A part, atom part, you solved it last term, but sorry, now we have a perturbation. The question is what to do with it. You go back to your toolbox. What are the things you know? Perturbation, right? So how about first order perturbation? Can we be that lazy? Do first order perturbation and get everything done? In fact, yes, only if you know how to choose the good basis set, the total angular momentum description, okay? That is the big picture of the story that follows. At this point, let us take a break, and then we will continue on with the mathematical derivation of the Hamiltonian spin orbit H, this thing, H spin orbit. The prime means that is the thing that will go into the perturbation term. All right. So let's have a break now.